Imagine a single shipping container packed with enough energy to power 5,000 homes for an hour. It is a silent, massive block of potential. But when that much energy is packed into lithium-ion cells, the physics of failure becomes a violent engineering puzzle. On March 24, 2026, engineers did the unthinkable. They intentionally triggered a total system failure in this 5-megawatt-hour giant. This wasn't just a fire, it was a deflagration test, designed to see if the structure could survive a literal internal explosion. To understand why this test is so difficult, we have to look at the chemistry. When a lithium-ion cell fails, it enters a state called thermal runaway, a self-sustaining feedback loop where heat creates more heat faster than it can be dissipated. As the temperature spikes, the liquid electrolyte inside the cells doesn't just burn, it vaporizes. This creates a high-pressure cocktail of flammable gases like hydrogen, carbon monoxide, and methane, all trapped inside a sealed steel box. Think of it like a pressure cooker with no safety valve, but instead of steam, it's filled with rocket fuel. Within seconds, the internal pressure can reach levels that would shred standard industrial housing like it was made of paper. The challenge for SolaX wasn't just stopping the fire, it was managing the physics of a firestorm that wants to expand at supersonic speeds while keeping the heavy steel doors from becoming projectiles. The ORI 5-megawatt system uses a high-density cell arrangement, which is great for the grid but dangerous during a failure. If one cell goes, it can trigger its neighbor in a domino effect that consumes the entire 20-foot container in minutes. This is where mechanical engineering meets disaster management. The goal isn't to save the batteries, they're already lost. The goal is to save the surrounding infrastructure and any people nearby by controlling the explosion's path. But how do you vent a 5-megawatt fire without letting the entire container collapse? That requires a piece of engineering that is both incredibly strong and intentionally weak at the exact same time. In the March 2026 test, sensors recorded the exact moment the internal pressure hit the critical threshold. At this point, the air inside isn't just hot, it's dense with unburned fuel waiting for oxygen to turn it into a fireball. If the doors were to blow open, oxygen would rush in, causing a backdraft that would level everything within 50 feet. The engineering solution is a masterpiece of pressure relief dynamics that SolaX calls their active venting system. By the end of this module, you'll see why the March 24th success wasn't just about surviving a fire. It was about proving that we can safely store massive amounts of energy right in the heart of our cities. The secret lies in the shell. Most containers are just corrugated steel. The ORI is a multi-layered fortress designed to flex without breaking, absorbing the initial shockwave of a cell rupture before the vents even have time to react. It's a delicate balance of physics. Too much venting and you feed the fire. Too little and the container becomes a bomb. SolaX engineers had to find the Goldilocks zone of pressure relief. Now, let's dive into the actual hardware that makes this possible, the pressure relief structure that saved the day during the 2026 deflagration test. To keep the main shell intact during an explosion, engineers use a concept called sacrificial venting. These are specific panels on the roof designed to fail at a precisely calibrated pressure, long before the steel walls reach their breaking point. Think of it like the crumple zone on a car. By allowing a small, controlled part of the structure to break, you protect the integrity of the whole. In the SolaX ORI, these vents are located on the roof to direct the blast upward, away from people and equipment. But there's a catch. When those vents open, they don't just release gas, they release a flamethrower of ignited electrolytes. The engineering must ensure that these flames don't spread to the rest of the unit. The vents themselves are equipped with flame arresters, dense metal meshes that allow gas to pass through, but are so cold and have so much surface area that they suck the heat out of the flame, extinguishing it instantly. It's the same principle used in minor safety lamps from the 1800s, scaled up for a 21st century energy giant. By cooling the gas below its ignition temperature, the arrestor prevents an external fireball. During the March 24th test, these arresters had to handle temperatures exceeding 1,000 degrees Celsius, while maintaining their structural shape against a supersonic gas flow. While the roof is venting, the doors have a different job. They must stay shut at all costs. If a door latch fails, the container loses its pressure management capability, and the explosion becomes omnidirectional. SolaX uses a reinforced explosion-proof hinge system. These aren't your standard shipping container hinges. They are over-engineered blocks of forged steel, designed to withstand thousands of pounds of lateral force. In the 2026 test, high-speed footage showed the doors bowing outward by several centimeters under the pressure, then snapping back into place as the vents relieve the stress. It's like the container is breathing.
To ensure the gas reaches the vents, the internal layout of the ORI system is designed with flow channels. These are empty spaces between battery racks that act like chimneys, guiding the explosive gases towards the roof. Without these channels, the gas would get trapped in pockets, creating localized hotspots that could melt through the container floor or walls. The engineering here is about fluid dynamics in the most extreme environment imaginable. Every millisecond counts. The time between the first cell rupture and the vent's opening is less than the blink of an eye. The system is purely mechanical, no sensors or electricity required to trigger the vents.
This passive safety is critical. In a real-world disaster, the power might be out and the control systems melted. The SolaX ORI relies on the laws of physics alone to save itself. The March 24th test proved that this mechanical breathing works perfectly, even at the massive 5-megawatt scale. But there was one more secret weapon tested that day, a material science marvel that protects the ground itself. Next, we look at the single-use shield, the final line of defense between a 5-megawatt explosion and the environment.
Beneath the battery racks lies the ORI's final secret, a single-use ablative shield. This isn't just a floor, it's a sophisticated material designed to sacrifice itself to protect the concrete pad and the soil below from extreme heat. Think of it like the heat shield on the bottom of a space capsule. As the fire burns at 1200 degrees, the shield material undergoes a chemical change, charring and expanding to create a thick, insulating barrier of carbon. This process, called intumescence, allows the shield to absorb a staggering amount of thermal energy without passing that heat through to the ground. It keeps the structural foundation of the power plant perfectly intact.
But the shield does more than just block heat. It's also designed to capture and neutralize the toxic electrolyte rain, the liquid chemicals that leak out of damaged cells before they can seep into the groundwater. The material contains reactive agents that bind with heavy metals and acids on contact. During the March 24th test, post-explosion analysis showed zero chemical leakage beyond the container's footprint. This is a massive win for environmental safety. It means these 5-megawatt units can be placed in sensitive areas, near rivers, farms, or residential zones, without the risk of long-term soil contamination.
The 2026 test wasn't just about the hardware, it was about the data. Thousands of high-speed sensors mapped the explosion in 3D, allowing engineers to refine the next generation of energy storage. What they found was that the ORI system didn't just survive, it exceeded safety margins by 40%. The pressure relief structure and the ablative shield worked in perfect harmony to contain the most violent event a battery can experience. This success has paved the way for gigawatt parks, massive clusters of these units that can replace coal and gas power plants entirely, with the confidence that they are physically incapable of a catastrophic blowout.
The engineering behind the SolaX ORI 5 megawatt-hours is a reminder that the transition to green energy isn't just about chemistry, it's about mechanical brilliance. It's about building boxes that can dance with fire and win. By mastering thermal runaway, pressure dynamics, and material science, engineers have turned a potential bomb into a reliable pillar of the modern electrical grid. It is a silent revolution happening inside these steel containers, a world where massive power is finally matched by massive safety.
Next time you see a large industrial container at a substation or a solar farm, look closer. You might be looking at one of the most sophisticated pressure management systems ever built. Behind that simple steel shell is a masterpiece of material science, designed to keep the lights on and the world safe, no matter what happens inside. Now you know the physics of the firestorm and the engineering that tamed it. Because at 5 megawatt hours, safety isn't just a feature, it's a work of art.